Hello, today I'm going to present the paper Clank, Architectural Support for the Intermittent Computation. Now just to give a brief introduction, energy harvesting is a method of drawing power from the environment rather than relying on fixed power sources like batteries. However, it often provides insufficient power for long-running computation, leading to frequent power losses and program restarts. Now, this limitation hampers the execution of programs and necessitates careful consideration by programmers. Batteries are also a major limitation because they are bulky, expensive, and have limited lifetimes. This paper proposes Clank, an architectural solution to enable existing programs to run efficiently across power cycles on intermittent harvested energy. Now, just to give a brief background, previous approaches to addressing the limitations faced significant hurdles. For example, in continuous checkpointing to non-volatile memory resulted in substantial overhead, which impacted the system performance. Similarly, compiler-based decomposition, though it was a potential solution, demanded significant programmer effort due to limited support from static analysis tools. Also, implementing a non-volatile processor incurred overheads in terms of area, power, and performance, hindering its practicality, and thus was introduced Clank. The key concept introduced to overcome these challenges is idempotency. Idempotency focuses on ensuring that instruction sequences are restartable while preserving input values. Idempotency enables the establishment of arbitrary restart points across power cycles, facilitating seamless resumption of operations. By preserving these input values, idempotency ensures that the system can restart from any point without losing essential data or progress. Now, just to give an overview of Clank. Clank utilizes lightweight hardware buffers to dynamically monitor idempotency during execution. When idempotency violations are detected, it triggers the checkpointing of volatile state data to non-volatile memory. The execution process is dynamically decomposed into restartable idempotent sub-executions linked by these checkpoints. Also, optional watchdog timers are employed to manage the trade-off between the overhead of checkpointing and re-execution. Additionally, compiler support is implemented to alleviate the burden on hardware buffers, thus optimizing the efficiency of the system. Now let's look at the key components of Clank. The key components of Clank are the idempotency detection logic, the write-back buffers, the read and the write-first buffers, the watch and the watchdog timers. Now let's look at the idempotency detector. At the crux of the Clank's functionality lies its robust idempotency detection mechanism. Idempotency violations which occur when a write operation follows a read to the same memory address are meticulously tracked and identified by specialized buffers and detection logic. The read first and the write first buffers play a pivotal role in tracking the order of memory accesses, enabling the detection logic to promptly identify and flag any violations occurred during the program execution. The read first and write first buffers. The read first and write first buffers within Clank's architecture serve as crucial components for efficient idempotency tracking and detection. These buffers are designed to manage memory accesses and track the order in which read and write operations occur during the program execution. The read first buffer specifically tracks memory addresses that are first accessed by read instructions within a given sequence of program instructions. It essentially stores the addresses that are predominantly read dominated. Conversely, the write first buffer focuses on memory addresses that are first accessed by write instructions, indicating the write dominated locations within the program's memory space. Now, during the program execution, the Clank's idempotency detection logic continuously monitors these buffers. And if a memory access involves a write operation to an address that was first accessed by a read instruction, as tracked by the read first buffer, the detection logic identifies that this is an idempotency violation. Similarly, if a memory access involves a read operation to an address that was the first accessed by a write instruction as tracked by the write first buffer, it may also signal an idempotency violation depending on the Clank's configuration and policy. Now, in addition to these buffers, Clank employs the dedicated detection logic to monitor memory accesses and detect idempotency violations. This detection logic continuously checks the contents of the read first and the write first buffers during the program execution. If a memory access involves a write operation to an address first accessed by a read instruction or vice versa, it signals an idempotency violation. Now, upon detecting an idempotency violation, Clank takes the appropriate action to ensure program correctness and reliability. Depending on its configuration and policy, Clank may initiate a checkpoint to save the program state, allowing for a rollback to a consistent state in the event of a future power failure or any interruption. This proactive approach to idempotency detection and handling is essential for maintaining the integrity of the programs running in intermittent computing environments where power cycles and interruptions are prevalent. Now let's come to the write back buffer. The write back buffer is a critical component of Clank's architecture which is designed to optimize checkpoint frequency and mitigate the overhead associated with idempotency violations. Idempotency violations occur when there's a discrepancy between the order of read and write operations to a specific memory address within a sequence of program instructions. The write back buffer serves as a temporary storage mechanism for idempotency violating writes, allowing the Clank to delay committing these writes to non-volatile memory. When an idempotency violation is detected, instead of immediately updating the corresponding memory address in non-volatile memory, Clank stores the updated value in the write back buffer. This delayed commit strategy effectively extends the execution of idempotent sections beyond their natural limits. By leveraging the inherent volatility of the write back buffer, Clank ensures efficient rollback during power off periods. During power on, the write back buffer contents are automatically discarded, facilitating a clean state for program execution without the need for explicit cleanup operations. Additionally, the write back buffer helps alleviate the need for frequent checkpoints by allowing Clank to consolidate multiple idempotency violating writes before committing them to the non-volatile memory. This reduces the overall number of checkpoints generated during the program execution, leading to improved efficiency and reduced overhead. Overall, the write-back buffer plays a crucial role in the Clank's ability to handle idempotency violations efficiently and optimize checkpoints frequently. Ultimately, it contributes to the system's reliability and performance in intermittent computing environments. Then we have the address prefix buffer. Now, the address prefix buffer is a specialized component within the Clank's architecture designed to optimize memory utilization and reduce redundancy in the memory address tracking. It, the, It addresses the spatial locality of the memory accesses observed during the program execution, especially in intermittent computing environments where power cycles and interruptions are common occurrences. Unlike the traditional approaches that track entire memory addresses, the address prefix buffer selectively stores only unique address prefixes, effectively reducing the storage requirements and conserving valuable hardware resources. This buffer recognizes that many memory addresses share common most significant bits due to spatial locality, especially in systems with limited memory capacity. For example, in Clank's implementation, each buffer entry stores only the least significant bits of a memory address along with a tag that points to one of the entries in the address prefix buffer. This design choice significantly reduces the storage overhead compared to storing entire memory addresses in each buffer entry. By deduplicating the common address prefixes, the address prefix buffer makes Clank's in-hardware buffers more efficient, enabling them to store more unique information with fewer resources. However, it's important to note that buffer overflows in address prefix buffer may trigger additional checkpoints, necessitating careful management to maintain the system stability. Overall, the address prefix buffer plays a crucial role in optimizing the memory utilization and improving the efficiency of Clank's memory address tracking, ultimately contributing to the system's reliability and performance in intermittent computing scenarios. The other crucial part of Clank are the watchdog timers. Watchdog timers are essential components which provide crucial functionality to enhance the system reliability and performance in intermittent computing environments. These timers serve two main purposes: ensuring software makes, for, makes forward progress and balancing checkpointing and re-execution overhead. Now let's look at the progress watchdog. The progress watchdog is instrumental in ensuring that software continues to make forward progress within a power cycle, despite the unpredictable nature of the harvested energy. In intermittent computing scenarios, there is a risk that long idempotent sections could lead to repeated restarts without completing the execution before the next power cycle. To mitigate this risk, the progress watchdog intervenes by breaking long idempotent sections with superfluous checkpoints. By inserting checkpoints strategically, even during short power on periods, Clank ensures that software can make progress and complete execution tasks efficiently. Now, this progress watchdog operates dynamically and automatically, responding to changing power conditions without requiring user or programmer intervention. Initially disabled to conserve power and avoid necessary checkpoints, it becomes enabled during the system initialization to facilitate forward progress. The second watchdog timer is the performance watchdog. The performance watchdog is responsible for optimizing system performance by balancing the checkpoint and re-execution overhead. In intermittent computing environments, Clank aims to maximize the number of instructions executed between checkpoints to minimize energy consumption and improve efficiency. However, excessive intervals between checkpoints can result in increased re-execution overhead, potentially offsetting the benefits of checkpointing. The performance watchdog addresses this challenge by dynamically adjusting load values based on program characteristics and runtime conditions. By calculating the optimal load value that balances checkpoint and re-execution overhead, the performance watchdog ensures near optimal total overhead during program execution. This meticulous optimization process contributes to Clang's efficiency and effectiveness in intermittent computing scenarios. In summary, the watchdog timers play a critical role in Clank's architecture, providing proactive monitoring and control mechanisms to ensure system reliability, forward progress, and optimal performance in intermittent computing environments. Now, Clank system implements several optimizations to boost performance, which include ignoring false write operations, then efficiently tracking the duplicates, and skipping unnecessary processing in text segments. These optimizations optimize the execution flow, enhancing overall efficiency. Additionally, compiler support is given, which aids in the process by inserting checkpoint and startup routines and marking the system accesses as idempotent, thereby alleviating the pressure on hardware buffers. Now, due to these enhancements, the code's overall size sees a modest increase, averaging around 5%. Now, to go a little bit more in detail on the Clank compiler. The Clank compiler plays a crucial role in facilitating the efficient execution of programs in intermittent computing environments by inserting software routines and optimizing program behavior to align with the Clank's hardware architecture. Now, first is the checkpoint routine. The primary software routine inserted by the compiler is the checkpoint routine. This routine is responsible for backing up the program state residing in volatile memory to non-volatile memory, ensuring data integrity and resilience against power interruptions. The checkpoint routine operates in two phases. First, it saves volatile state to non-volatile memory, and then it resets the clanks in hardware buffers and watchdog timers. By leveraging double buffering and careful management of checkpoint pointers, Clank ensures the atomicity of checkpoint operations even in the event of power cycles during checkpointing. Additionally, in cases where a write-back buffer is present, the checkpoint routine incorporates additional steps to handle checkpointing complexities effectively. The next routine that the Clang compiler provides is the startup routine. Upon device initialization, the startup routine plays a critical role in restoring state from a checkpoint in non-volatile memory and initializing power and device state accordingly. Unlike the traditional startup routines which simply initialize the devices and pass control to the main program, Clang startup routine must handle restoring the state from checkpoints and configuring the watchdog timers. The compiler generates the initial checkpoint, simplifying the startup routine's complexity and ensuring seamless execution across power cycles. The third is bridging the semantic gap. The Clang compiler bridges the semantic gap between software and hardware by optimizing memory accesses to enhance the Clang's hardware effectiveness. By identifying memory accesses that do not impact idempotency, the compiler informs the hardware to ignore these accesses, thereby reducing the overhead associated with tracking unnecessary memory operations. While current static idempotency analysis passes are limited in scope, Clank's dynamic analysis enables more comprehensive analysis across multiple functions, paving the way for future compiler optimizations to improve Clank's performance further. In summary, the Clank's compiler plays a pivotal role in optimizing program execution for intermittent computing environments, ensuring program correctness, reliability, and efficiency in the face of power interruptions and fluctuations. Now, the evaluation process of Clank involved tailoring the system for the ARM Cortex M0 Plus low power microcontrollers and exploring over 1 million hardware configurations. Formal verification was conducted on the Verilog implementation, followed by testing across 23 embedded system benchmarks. Comparative analysis with approaches like Dino and Ratchet were also performed alongside an examination of checkpoint versus re-execution overhead trade-offs. In highlighting the key benefits of the system, it becomes evident that it offers seamless execution, ensuring existing programs run efficiently across power cycles with just a 2.5% overhead. This reliability is crucial for uninterrupted operation in critical environments. Additionally, the system's plug-and-play integration capability eliminates the need for programmer intervention or code changes, streamlining the adoption process. Moreover, with the only minor hardware adjustments required, amounting to a mere of 1 to 2% area overhead, the system demonstrates cost-effectiveness and scalability. Its versatile adaptability further enhances its appeal, effortlessly accommodating various volatile and non-volatile memory configurations without compromising the performance. This adaptability makes it flexible solution suitable for diverse applications and environments. Thus, in conclusion, Clank represents a significant advancement in architectural solutions by introducing a novel approach that efficiently leverages dynamic hardware idempotency tracking. Unlike previous methods reliant on compilers and software, Clank outperforms them by harnessing hardware-level mechanism, leading to superior performance and effectiveness. By dynamically tracking idempotency at hardware level, Clank offers a more robust and reliable solution, ensuring the correct and efficient execution of programs. Moreover, its innovative design enables new capabilities specifically tailored for energy harvesting devices, opening doors to enhanced functionality and efficiency in this rapidly evolving field. Overall, Clank stands as a pioneering architectural solution that not only outperforms the existing methods but also unlocks new potentials for energy harvesting technology. Thank you.